All right, so we're going to get into these suggested problems from the syllabus here. These problems go with the lectures for 217 and 219, which are corresponding to homework 5. So I'm going to do these just because homework is graded, and for academic integrity reasons, I like to help you guys as much as possible, but I need to cover my own ass, and so I'm just going to do these, and hopefully you guys hearing my thought process and seeing me work through them will help you enough that you can figure out the homework on your own then. So getting into this first one here, there's actually a couple parts to this one, and I have them on separate pages for the different geometries. I have the pictures and everything in there, but the problem number is 5.6, and this is in the 8th edition of the Bergman Heat and Mass Transfer textbook that we use. So in these problems, it tells you to calculate the characteristic length, L sub c, and the corresponding Biot number, which is usually we just write BI, um, for each of these objects given the information or the conditions. So this first one is relatively straightforward. It's just got the little bit of complicated geometry with the toroid, that donut shape. But you'll see that some of these other ones are a bit less straightforward, and so just I'll kind of point that out when there's some interesting, clever things you have to do. But other than that, just strap yourself in and enjoy the ride. So in this first one, like I said, the most complicated part is just figuring out the geometry. So um, let's start by just saying, here, our Biot number is going to be H L sub C over K. So this is this is not the first time that this has come up. He's mentioned it before, usually when we were talking about thermal resistances, because this is actually a ratio of it would be your conductive resistance over your convective resistance, right? So your conductive resistance is K over L. Wait, nope, sorry, I lie. It's L over K. Your convective resistance is 1 over H, so then you can, rearrange it, HL over K. And you get this dimensionless quantity. So that's just a little tidbit. If you ever forget what order they go in, like is it H on top or K on the bottom or what it is, that can kind of help you. I'm sure you guys will just eventually you'll just remember it, and it is what it is. So HL over K. So your H is your convective heat transfer coefficient, which in these problems in chapter 5 and previously we're always given that. Eventually we're going to have to calculate that on our own, but for now we're given that. L sub c is a characteristic length, which is the only thing that you really have to do any sort of thinking with on these for the most part. And then your K is your conductive heat transfer coefficient, which in this case we're given, and I have it written down there. So this L sub c value, we're usually going to get that by taking a ratio of volume to the area involved in the heat transfer. So the reason why that area has to be so complicated is because you'll actually see in one of the later cases in this first problem that you don't necessarily have to do this only for convection. It can work for, well, I don't know where I was going with that because it doesn't really matter. Basically, that area is going to be your surface area, but you have to be careful that you're only capturing the surface area that's actually exposed to the convection or the radiation for your given problem. And I know that's kind of vague and it doesn't make much sense, but as we go along, I think it'll become more apparent, and I'll be able to point out like situations where you have to, think about it a little bit more. So in this first one, if you look at this shape, right, when I have a complicated thing like this, and of course, like, I mean, if you know the formula for the volume of a donut shape like that, you can just take your diameter and plug it in, I'm sure. But well, you wouldn't actually be able to do it with just the diameter. You still need that cross-sectional area or something like that. But something that kind of helps me is like in the back of my mind when I'm trying to figure out a volume, instead of remembering a bunch of formulas, I just think that, at the end I need to get a length dimension cubed. And the easiest way to do that is to take some sort of cross-sectional area if it's constant throughout the shape, and in most of these geometries it is. You calculate that cross-sectional area, and then you just multiply it by either the length, or in this case it's actually going to be a circumference because it's round. So if you look at the picture here, this shape is just this little circular cross-sectional area, the value of a sub c that we're given in the problem. And so I kind of did a half-assed unit conversion there, from the millimeters squared to meters. I mean, like, well, how do I want to say this? And I want to apologize now that this is going to be choppy, but I wasn't messing around with taking multiple takes because it's already getting late and I'm tired. Um, all you have to do is go ahead and plug that in the calculator. And just a forewarning, in these problems, I'm not going to go all the way through with actually computing the numbers, because you can go into the files page on Canvas and get the solutions that he has posted if you want to double check your numbers. I mean, I personally think at this point, I can't teach you how to use a calculator. I know that might sound pompous and rude and stuff, but I hope you guys understand. I'm not messing around with punching stuff in a calculator or switching my screens back and forth so I can show you the MATLAB that I use to do these calculations. It's up to you guys, but I can show you how to set them up. So anyway, with all that being said, I have a sub c there, and I'm showing what you need to do to convert to square meters from the millimeters squared. So just be careful there. You get that whole conversion factor squared, so it's not just like a straight millimeters to meters, it's millimeters squared to meters squared. So you take the whole thing and then you wrap it in the parentheses and square that whole fraction before you would multiply it by your cross-sectional area. So to get back to the volume discussion, so you're really just taking that cross-sectional area and multiplying it by a length, or like I said, in this case it's round, so it's a circumference. And I'm just going to use the average circumference there, because it just makes sense to do that, and it's close enough for what we're doing, and two, that's really the only thing we're given information on. So we couldn't really, I guess you could figure out the outer and the inner, but the way that we're going to do it, I'm just going to use that diameter big D that we're given there. So the perimeter of that, the circumference of that, is pi d, big D. And then you just multiply that by that cross-sectional area, a sub c, that we're given, and boom, that's going to be a volume, because you have meters here, and this is meters squared, and you get meters cubed. Okay, so then this is the more complicated part in this case. We got to get this area exposed to the heat transfer. So I think it's helpful if you look at that, if you look at the a sub c section over here, and I'll erase some of that. We have that round cross section that goes the whole way around that donut shape. So you really, when we're looking at the area exposed to the heat transfer, we want this outer surface, right? But when we're looking at it in 2D there, that's not the whole surface area. That's just around one little, slice of it. So we need to get all the slices. So we got a little bit of a predicament here, because we're given a sub c. If we had the diameter of that circular cross section, we could just do pretty much the same thing as what we did with the volume, where you calculate the perimeter and then you multiply it by the whole length around, and then boom, we got a cross-sectional area. Or not a cross-sectional area, surface area, because in this case we just want the whole surface area of that donut, because that's what's exposed to the convection. But we don't have that. However, since it's a circular cross-section, we can take a sub c, and we know that the area there, the cross-sectional area, is pi, and then it's r squared. So I'm going to write it like a little d over 2 squared. You can have pi over 4d squared, or you can just have pi r squared and solve for r, and do what you want with that. But you have this, and then we can actually solve this for the little d. So it's AC over 4 pi, and then it'll be the square root of that. I know that's a little bit of, that's kind of quick with the algebra in one step there, but I mean, you go back and just pause the video and think about it or look at it or write it out yourself. Pretty sure that's right. And that's what I have in my notes here, and I got the same answer by following what I have in my notes as what he has in the solutions posted. So, pretty sure that's right. So now that we got that, well, actually, no, it's not right. Here I am saying I'm pretty sure it's right. So it should be, the 4 should be on top, because you're going to get a 4 on the bottom with that d over 2 squared, and you're going to multiply that over and divide by the pi and then take the square root, and that's going to give you the little d. And now with the little d, our perimeter is just pi times that little d, which we're going to fill it in as 4ac square, pi times square root of 4ac over pi there. And then the distance around the perimeter of that whole thing, the other dimension for this cross-sectional area, is the circumference of that whole donut again. So it's, we're taking, like I said, we're finding this perimeter, and then that length times this whole length is going to give you the surface area of that shape. And at this point, it's just, taking this and cleaning it up. You can cross some stuff out there, plug it in your calculator, and you get an LC. Then once you have the L sub C, your Biot number, going back to what we have over there to the left, is just HLC over K. You plug things in, and let me double check here. I got and I should have been more prepared. This is going poorly already. I get a Biot number of 0.004, and if this is less than 0.1, so you could use the lumped capacitance or case 1 or whatever you want to call it, the stuff that he showed us in lecture. You can use the assumptions there and solve the problem with, they were asking us to do more. So that's that one. Okay, on to the next one. So now hopefully I'm rolling here a little bit, and I'll be a little bit smoother and ramble less. So same thing, we want to get our Biot number, HLC over K. First, we got to find our LC, and our LC is going to be the volume over the area exposed to the heat transfer. And so volume here, it's rectangular prism. So we got little w, big W, which I put those lines on so you can, tell that it's a capital, times L. Pretty straightforward. And then the area exposed to the heat transfer is a little bit complicated. So here, depending on how you look at it, you can either include the ends, the gray ends there, or not. Well, I guess only one of them is gray, but there's one here, and then there's one at this end. You can choose to include those or not, depending on if we were actually doing this in real life and we had to figure something out. Depending on what the situation is, we may or may not include that, but I'll just include them here for the sake of including them. So the surface area of the long portion, not including the ends, is going to be the perimeter of the cross section. So that's 2 times big W plus little w, right? So that gets that length there, basically. And then that whole thing times L gets you the surface area of that portion. And then if you want to include the ends, we're going to add 2 times. Now, one of these areas is just little w times big W. And there's 2 of them, so that you just slap the 2 times on there, and bam, you got it. And like I said, you can choose to include that or not to include that. And then, at this point, you plug all that in the calculator, and then you go back, and once you get that number, you take your H that you're given. Another thing I forgot to mention is the problem says that it's 304 stainless steel. So you actually have to go under the back of the book and look that up. and um, the K's in the back of the book are given at different temperatures because, of course, the K varies with temperature. But I just assumed, well, and actually, now that I look at it again, it says if the temperature information is not provided, evaluate properties at T equals 300 Kelvin. Um, I forget now if I actually. I mean, this 10 is like an approximation. An approximation. I said that weird. Sorry. Because he just says that it's roughly 10. I mean, in this case, you're only using it to calculate the Biot number, and the only reason you're calculating the Biot number at the beginning like this is to make sure that it's less than 0.1. And if this is 10 or if it's 12, it's not going to make that much of a difference. If anything, it's going to be, if I remember right, it's actually a little bit greater, the value, but you guys can look that up and use the right one if you want, but I was being lazy and wanted to get through these. So that's it for that one. All right, on to C here. Okay, so this one's, it's a little bit complicated. So one important thing is in the book it says that so this aluminum tube is submerged in water, and that's what's providing your T infinity and your H there, your convection to the outer surface, but then it's plugged at both ends, trapping stagnant air inside, it says. So basically what all that means, what you're supposed to get out of that is that you're not supposed to account for convection on the inner surface there. So you're just looking at the outer surface. And this one is another one where you can decide to include or not to include the two end caps. In this one, it's even less of a big deal because the area of that end, with it being hollow and having that such a small thickness, like if you look there, the the thickness is what, 2 millimeters, 0.24 minus 0.2, and then it would be divided by 2 because you have it at each end in the dimensions there. I think that's what it would be, but my quick maths aren't that good sometimes. So the point of all that is that with being 2 millimeters thick, that's not going to be a very big area if you include those, so it doesn't really matter if you include them or not. So I'm going to opt to not do it just to make it easier to calculate LC. So volume over AHT. So here, your volume is going to be, once again, remember what I said, cross-sectional area times the length. So in this case, the cross-sectional area is big W squared minus little w squared, because you can take the area of I'm assuming that this is a square tube with the way that the dimensions are given. So you can take the area of like the outer square if you take the biggest dimension and subtract the area of the smaller inner square, and you get the area that's left behind, of course, which is what we care about. And then you multiply that by L to get the volume. Okay, and now the area exposed to the heat transfer is just one of these, same type of thing. It's like the perimeter of that times the whole length, and that's going to give you your surface area. So in this case, the perimeter is really easy. It's just 4 big W and then times the L. And once again, you can take this and clean up what you want and plug it in your calculator however you want to do it. Plug it into MATLAB, whatever you want to use, and then it's just HLC over K. In this case, it tells you what kind of aluminum it is, so you have to go and look up the K, equals something, and you plug it in, and then you check if it's less than 0.1 or not, and you can say like, yeah, we can use the assumptions or we can't. Okay, so 5.6D. So I'm gonna remember this time to talk about the little nuance in this one right off the bat. So you're only given a mass. You're not told what the material is, so you have nothing to go and look up right away what the K is. But what you can do is we can find the volume, okay? And the volume is going to be this cross-sectional area times the length. And maybe I should do that in my blue. So this cross-sectional area times the length for a cylinder. Okay, so it's going to be pi over 4 big D squared L. And you would compute that, get the number, and then you can find the density as the mass over the volume. And if you guys remember from, I don't know, chemistry or whatever, you can pick your poison when, I'm sure we've heard this a couple times in different classes, but density is some, like, that's a property that is, I don't even remember enough to before I say make a sweeping claim, but I'm pretty sure like you can always use density to identify a material, because it's like, I mean, at least in the stuff that we're dealing with, like you calculate a density and this value is going to be, I think if I remember right, when I actually plugged the numbers in to make sure I was doing it right, this exactly matches one of them in the back of the book, and it's like, I want to say it's like 316 stainless or something like that, stainless steel. And so then you get a K, and then once you have the K, we already calculated the volume there. Sorry, I'll leave the picture in view. And then remember, LC big V over AHT. And so this is pi over 4 D squared L. And the surface area is going to be, now we're going to take just the perimeter of that circle, that cross-sectional circle, times the whole length. And so that's going to be a pi big D L. And the L's cancel, the pi's cancel, the squared there cancels with that. And you get L sub C is equal to D over 4, which is R over 2, if you want to do it in terms of the radius. And that matches up with what he gives us in lecture. So, it's confirmation that I'm not bullshitting you guys. And I actually, I mean, at least on this one, I was able to know what I was doing. And I know my humor has been pretty dry thus far. If you guys could see my face, you would understand when I'm joking. So that was a joke, and it's okay to laugh. And I probably ruined it now, but I'm very lighthearted. So if it seems like I'm trying to be funny, I probably am. So please laugh so I can feel good about myself, even though I won't know if you laugh. Okay, anyway. Wow. That was awkward. Sorry. And same thing. At this point, Biot number HLC over K. So in these first bunch, it's just really like the most complicated part is like figuring out what K is based on them being tricky like this, or figuring out what AHT is and the volume is to calculate your LC. And the Biot number, it's just plug and chug at that point. All right, so now this one's funky because it's in an oven and you're talking about temperature surroundings. You're given an emissivity. So we're dealing with radiation off of this sucker here. No convection. All right. And so there's some energy stored, and that's not a T dot. It's like E dot out due to radiation rather than convection. So if you guys remember before, we kind of had a problem come up in lecture once where he did this funky math here to get, like, you can basically take radiation, right? So Q dot for radiation is the emissivity times sigma, which is that Stefan Boltzmann constant, which I'm going to write here. It's like 5.67 times 10 to the minus 8th. I have no idea what the units are on that. All I know is that it works out. And then this is times t to the 4th minus t surroundings to the 4th. And so first, remember, we have to take our temperatures. When we got these fourth powers here, we got to take our temperatures and convert them to Kelvin. So when you actually plug it into your calculator at the end, when we get the expression, make sure you have it in Kelvin. So your 18 here, you're going to be like plus 273, and the T initial is going to be 273 to get them to Kelvin. Okay, so this is the Q dot. So if you remember right, our Biot number, and I'm going to write that somewhere else here. Our Biot number is HLC over K. So now we're like, oh my God, what the hell are we going to do? We don't have an H. Like, we're not dealing with convection. But if you remember, there's a clever trick that he showed us one time, and I don't even know if it's really that clever, if it's just what you do. But you can take this here, and this is a difference of squares, right? So you can factor that to be t squared plus t surroundings squared times t squared minus t surroundings squared, right? Remember that from algebra. So it's like usually you're used to seeing it like this, and it's obvious it's a difference of squares, but fourth powers are squares too. It just happens that they're unsquared counterparts that you break it up into here are squares rather than just singles. And then we can do it again because here we have another difference of squares. And so ultimately you get that you can break this out into, it'll be t squared plus t surroundings squared times t plus t surroundings times t minus t surroundings. Okay, and the important thing here is this, all right? So we have like, think of it as like there's like a you know, there's a dividing line there. So we have t minus t surroundings, which looks a lot like our convection formula, because our convection is HAS times t minus t infinity. So that looks a lot like that. So we can take all the stuff to the left of that big thick blue line that I drew there, and we can treat that as like an H equivalent of due to radiation. All right, and this is the tricky part of this one. Okay, and so you're thinking, what t do we use here? Well, if we want to be the most conservative in our estimates, we use t initial, because that's going to be the biggest t, which is going to give us the biggest h, which is going to give us the biggest Biot number here, because the h is on top. So if h is bigger, the Biot number is going to be bigger. And remember, at the end of the day, when we're looking to see if we can use this case one type of analysis that we learned on Wednesday's lecture, the key is that this has to be less than 0.1. So if we use the t initial as our t for calculating this h equivalent, we're going to be getting our most conservative estimate, because we're going to be producing our biggest Biot number, even though, like, we're kind of well, of course we're approximating here. And so when you approximate, it's best to be conservative with your approximations. That way you don't ruin anything. So you take t initial, t surroundings, plug them in here, convert them to Kelvin before you plug them in, because we still have these squareds here. And you take your epsilon that's given and the sigma from the equation sheet, and I have it over here. Plug all that in, you get h. And then LC, you can do the volume over the area of the heat transfer. It's a sphere, so we know 4/3 pi r cubed over 4 pi r squared. And so you're going to get, this is going to be r over 3, which is d over 6, because we're given diameter like we are in every single problem, because who measures? Nobody can measure a radius, but all these formulas end up needing a radius, which is annoying. So d over 6, you take that and you plug it back in. The other thing is, like, if I was actually doing this, I would just go and say this, and then, like, from lecture or whatever. Like these common shapes like spheres and cylinders and slabs, you can just kind of, I would think that we're going to be allowed to just go right to that if we remember it, and say. So I just always stick stuff like that either from the book and show what equation or page, or from lecture and just say, like, from lecture, if I do something that's not necessarily obvious when I'm working on homework or whatever, so it doesn't look like I'm pulling it out of my ass. And then you take all that stuff, because I think we have everything. Yep, because we're given K, and you plug it all in and you get a Biot number, and it's whatever. So on to the next one. I'm already half an hour in and we're only on the first problem, so I'm sorry about that, but this stuff takes time to explain. So this one is the most complex of them all. It doesn't really, I don't know, it doesn't really make sense that they lump this in with this 5-6 problem, considering that they're just telling us to find the Biot number and the characteristic length, because here we're not given H, but we're given information about everything else. We're told the temperature of the stream, we're told the initial temperature, and then we're told the temperature of the surface after some time. So really what we need to do is we're just going to kind of say, you know, our bias is this, but we don't know H. So we're just going to assume that this is less than 0.1 for now. So then we can use this new analysis that we learned about. And so I'm going to kind of scroll this a little bit so I have more room. Okay. So if we draw our cylinder here, right, so we got our cylinder, and I'm going to draw a control volume around it. So that this blue is my control volume, right? So it doesn't really matter, just as long as it, you know, encircles the whole thing. So the whole premise of this, what we can do here when the Biot number is less than 0.1, basically what we're saying there is that based on the conditions, the temperature doesn't vary enough from the surface of the object to the center of it that we don't have to worry about the conduction like into or out of it, and we're just going to act like the whole thing's at the same temperature. And so the only energy term that cylinder has now is the E dot ST, which is due to the fluctuating temperature, that in this case, like, it's technically the surface temperature that's changing, but we just act like it's the temperature of the whole thing. And so then there's going to be an E dot out due to convection. So it actually does match up, like, based on the temperatures given. I mean, it starts at 200 and the T infinity is 20, so it is going to be an E dot out because that surface temperature is greater. But I could have drawn it as E dot out even if it isn't going to be, and as long as you do everything right, the signs will work out. So if we look at the actual energy balance, right, we have E dot in plus E dot G minus E dot out is equal to E dot ST, right? So there's no E dot in, there's no E dot G. Now, we're not told that, but we're not given any information that would get us anywhere close to figuring out what E dot G is. So that's a telltale sign that you can just, you know, act like it's not there. And I don't know that right now, with the knowledge that we have, I don't even think we could handle a situation if that had an internal generation like that. So definitely not there. So all we have now is minus E dot out equals E dot ST. Okay, and so then we come over here, we say, all right, E dot ST is going to be rho VC dt, because really that E dot ST is du, big U, where U is internal energy, dt, but we can, I don't really, he always kind of explains a bit about how we get from there to here, but I think for me, I just kind of, I don't know, at this point it's like rho VC dt is just burnt into my brain, and so I just kind of write it down. I don't really go through the steps of actually figuring it out each time. But if you look at the, like, if you were stuck, you could kind of piece it together by looking at the units, right? So you have kilograms per meter cubed times meters cubed times joules per kilogram Kelvin, and then dt. So that's dt is Kelvin over seconds. So the Kelvin cancels, kilograms cancel, meters cubed cancel, and you're just left with joules over seconds, which are watts, which in heat transfer, in these energy, well, there's two ways you can look at it. In heat transfer, we're like always pretty much talking about watts, or you could just remember, you know, it's all these things have, these E's have dots on them because they're energy that's flowing and moving over time. And so it's joules per second because that dot tells you got that time derivative, which is like seconds on the bottom. So however you want to look at it. So that's a little handy trick if you forget. You can kind of cheat a little bit if you forget, like, you know, is it rho C over V or the order of everything? You can kind of look at the units and get them to work out to what you need to be. my advice would be just to get it burned into your brain. So then E dot out is going to be an H surface area times T minus T infinity. Now this T is the surface temperature, which changes with time. So just remember that it's not just a static T. That's changed. The temperature of the surface is changing in time, or else we wouldn't have the problem. So then plug it all in. You got minus H A sub S T minus T infinity is equal to rho V C dt dt. Okay. Separate variables, so you get minus HAS over rho VC dt. I'm going to slap the plus C on there so I don't forget, because I already kind of see where we're going here. T minus T infinity. And now here you integrate, right? And on the left side, we're just going to get all those constants, right? Because none of them are changing with time. They're all constants in time. T, and then the plus C that I had in there, and then this is going to be, it's 1 over T minus a constant, so the constant doesn't really matter. It's just really, it's like 1 over T, and so that's going to be the natural log of all that stuff. All right, and then here, to make it easier, like notation wise, you know, we can invoke that theta stuff from before, where theta is an excess temperature, which is T minus T infinity. Like literally that's the definition of theta. So I'm going to do that just to make it easier to write it all. So what we end up with is that we have the log theta is equal to minus H A sub S over rho V C T plus C1, I guess we'll say. So it's more apparent what it is. That's a constant we need to find. But we have the initial temperature. So at T equal to 0, T is equal to 200. So then theta is going to be 200 minus 20. And you can just kind of call this a theta initial for now, or maybe a theta naught. And so you plug 0 in here, we're going to have the natural log of theta naught is equal to 0 plus C1. So C1 is log of theta naught, all right? And so when we can rearrange here, ooh, I'm running into the next part of the problem for theta. So this, you can rearrange, subtract that over. It's going to be lots of rewriting here. So that, and then you can use the, if you subtract two logarithms, the same base, so ln of something minus ln of something else, you can rewrite those as that. So it's a little bit nicer, cleaner, more compact way to write it, and we always like more compact over rho VCT. All right, so that's that. And so then what you would do is you're given the temperature then at a certain time, and so you'd say at T equal to 225 seconds, theta is equal to now, what's the temperature that we're given? So theta would be 100 minus 20, so it's 80, and you have our theta naught from before. So we know, we know all these other things because we're either given them or we can calculate them based on the geometry. And so you would take this and you're going to solve it for time. So you have rho VC over minus, don't forget the minus because I was doing that earlier and I was like, what the hell am I doing getting negative time? Rho VC over HAS ln of theta, and we'll call this like theta 2 over theta naught, okay, equals T. You plug all that in a calculator and you get what you're looking for, which is the time. And it's like, what do I want to say? I don't know if I actually, maybe this is the one that I didn't actually run it and see what the number is, but you can find the number in the solutions that are posted. Just to comment, what was I going to say here? So an interesting thing you notice here, and this will come up in a later problem, you have this volume over A sub S thing where you would have to, you think you have to calculate the volume in the A sub S, but if you remember, that's just our characteristic length. And I'm sorry that I'm writing it way up here. Let me scroll down so you can still kind of see that. That's just that characteristic length, which technically in this case, you probably should have calculated at the beginning to see for the buy it number, just to make sure it was reasonable that we could assume that it's probably less than 0.1. And so, oh my gosh, I'm a goofball too. I didn't want to tell you guys to solve this for t. So all that goes out the window. I'll come back to that characteristic length point that I wanted to make. What was I saying? So here we're actually doing all this because we don't know what h is, right? And so at this step, we have rho vc. We know t. Like I'm already, should have been like ding ding ding. I'm an idiot. I'm writing it right there. So we solve this. We want to solve this guy for h. So it's actually going to be rho vc over negative rho vc over as t ln of theta 2 over theta naught is equal to h. And now you plug all that in and you get it. But my point that I was going to make still stands. So there's this guy here. So in this case, we could, since we're dealing with it's a cylinder and we're given the diameter and the length. No, we're not actually given the length, but okay. So that's part of the point that I want to make. Like the volume over the surface area there, if you remember right, the characteristic length for a cylinder is r over 2, or it's d over 4. So the length, you see, doesn't come into play at all. And it can be helpful sometimes if you notice that you never have to count. Like in these problems, it's always like either v over a sub s or it's a sub s over v, which in either case it's either LC or 1 over LC. And we define LC as that v over as, but it doesn't have, since this buy it number really just has that LC because it needs a length dimension, like something with the dimensions of length to make it dimensionless. And so sometimes like you might hear it called a length scale. So like that implies it's just there to add something about a length in the problem to that number. And so that's really convoluted, but the point is that we don't necessarily strictly have to calculate that as like v over a sub s. Like another way you could look at it is like we're assuming that temperature is uniform through like some direction. And so in this case, like if you look along the radius of the cross section, if I go back up here to the picture, like we're saying that from here to here, that r, the temperature along that direction doesn't change much. And so like that dimension has to be coming into play with that LC somehow. I know that's not a very good explanation, but the point is that like you'll see later on there's a problem where we're given stuff and we can't really calculate a volume or a surface area, but it ends up being fine because we don't really care about the actual volume or the surface area. We just care about that ratio of the two, which ends up exposing some kind of length dimension with usually a constant factor. Like if it's complex geometry like this, like you see you get the half there, or whatever. Like there's but it's, the point is that you get the d or the r, and the constant factors are just based on the geometry. So that first part is done. Now part G of this is to go back and then actually to finish this up, once you get the h, it's going to be a number, and you should check that if you go back now and calculate the buy it number with that h, that should be less than 0.1, or you got to move on to some other kind of analysis, because your assumption that you made to solve for that h was actually incorrect with the h value you get, which tells you that your thing is not, like, you're not meeting that assumption. If you solve for an h by making an assumption and then that h breaks the assumption, you got to do something else. But in this case, in this section, this is what we're supposed to be doing. So I'm pretty sure if I remember right, it actually works out that that was an okay assumption. Then in part G, you basically repeat the whole thing, except now instead of your D being 0.02 meters, it's 0.2 meters. And so you basically just recalculate your Biot number, make sure it's less than 0.1. And in that case, well, let me backtrack. You're going to repeat the whole thing and find H again and then plug all the new numbers in and make sure it's still less than 0.1. And I didn't actually go through and do that because it's essentially the same stuff with just a little bit changing. I mean, you don't even really have to go through the energy balance to rederive the, you know, like, you don't have to go through and re-derive this because this doesn't depend on, I mean, H is H and A and V are in there and they, of course contain that diameter that's changing, but it, like I said, it doesn't end up really, like, we get to the end here and we don't really care. Like, nowhere along the line does that whole expression and process change because the diameter changed. It just changes the numbers and you calculate the new H and then make sure that the Biot number is less than 0.1. So I'm done flapping my gums about that one. So here we are, we're on 5.7 now. So that was all one really long first problem. We are 46 minutes in, so I'll try to hurry up here and hope this has been helpful thus far. But I think I'm on a bit of a roll now, and so hopefully I keep moving quicker. So here, let me flip my page on my text here that I have up on my computer. So we have steel balls that are 10 millimeters in diameter. So I have that, I have all these stats written down to make it easy, so I don't have to keep looking back and forth. But I just want to read you the context so you have it. And this is 5.7 in the 8th edition of the text, if you want to look at it yourself. So steel balls 10 millimeters in diameter are annealed by heating to 1150 Kelvin and then slowly cooling to 450 Kelvin in an air environment for which T infinity is 325 Kelvin and H is equal to 25 watts per meter squared Kelvin. And then it tells you to assume that the properties of the steel are K is equal to 40 watts per meter Kelvin. Density rho is 7,800 kilograms per meters cubed, and the C, which remember here it doesn't matter if it's CV or CP because we're dealing with solids that are incompressible and so they don't change. It's C is C for a solid, and so that's 600 joules per kilogram Kelvin. And it wants you to estimate the time required for the cooling process. So we want to know how long it takes to get to 450 Kelvin based on the information we're given. So the first step here, as is pretty much always the case, we want to look at an energy balance. So I'm going to redraw my circle. I don't know why I'm redrawing it down here, but we're going to draw it sloppier so it makes sense that I'm redrawing it. So I got my sloppy circle, and remember, so this is I'm drawing a circle, but this is really a sphere, okay? But, so I'm drawing a circle, okay? So this has a diameter of D, right? So it's exposed to convection, so we're going to say we got an E dot out of convection, right? Because we got like air flowing around it here to cool it off. It's got T infinity H, right? So we got E dot out convection. And, well, so the temperature is changing with time, and we need to find the time, so we got a transient problem. We don't have steady state. So we got to go and look. We got to say, all right, let's calculate our Biot number. Okay, so our Biot number is HLC over K. So we got to get our LC. In this case, I'm just going to say LC is D over 6, or it's R over 3 from lecture. Okay, or you guys can quick scribble that out. Like, you should be pretty good at that by now after watching me do all those and hopefully processing it and stuff. You probably are pretty quick with getting those now if you actually had to figure it out. So you plug the numbers in and you get it, and the Biot number here, I forget what it is, but it's less than 0.1. Okay, and I don't really need that much less, but it's definitely less than 0.1. So we can use the lumped capacitance case 1 type analysis, which you could have inferred that was going to be the case because that's what section of the book we're in and that's all we really know how to handle these. But it's just, you got to do this stuff to show that the assumption you're making is okay. And so I kind of explained how this all works. So it's just, I think it's important to think about why we're doing this and what, and so you can understand it for when there's more than just this type of problem that can come up, and so you know like why this is the case. So remember, we're by the Biot number being less than 0.1, basically that tells us that it's the temperature change from this surface to the center, like, and throughout this sphere, the delta T along the radius there, in that, like, the delta T temperature change through that whole body. So the temperature change with respect to the radius, like the radial dimension, the temperature change with respect to space, however you want to look at it, is so small that we can basically act like there's like it's zero, and that um, the surface temperature is the same as the temperature of the body throughout. Okay, and so in that case, there's just going to be energy storage happening inside our sphere there, in our, and it's actually technically in our control volume, the pink control volume that we drew, or not pink, blue control volume we drew there. So if you remember, I'm going to jump right to, you can do the whole energy balance thing, but I'm going to jump right to here. E dot out convection is going to be equal to E dot ST. So, basically it's the sum of the energy in minus the sum of the energy sigma E. That's not very good looking. E dot in minus E dot out plus E dot G is equal to E dot ST. And there's no E dot G and there's no E dot in. So this is what it is. All right, and then I'm going to be a little bit quicker here too. So E dot out convection is H A sub S T minus T infinity. And remember, that T is a function of time, so it's not just any, that's going to be changing. And then E dot ST is going to be rho V C dt dt. Okay, get all this H A S over, what am I doing? So I'm already kind of cheating with the algebra, but this, you're going to get, okay, and then this will just be a dt. So if you do plug all that stuff in, you do the algebra, don't forget the negative sign on the E dot out on the left side there. You divide the rho VC over, this is what you get. All right, you integrate, okay, minus rho VCT. Oh, shoot. Completely forgot. Yeah, see, this is what I get for trying to be quick. There's a T minus T infinity on the bottom there, which is very important that you do not forget that. Let's add a constant there to the left side. And then this is going to be your natural log of T minus T infinity. Okay, sorry about that slip up. That's really important, though. Okay, so then I'm going to do what I did before and call this theta from here on out. And so at T equals 0, your T is 1150 Kelvin. Yeah, 1150 Kelvin. And so, you would get theta, which is going to be like 1150 minus, what's the temperature of the air? 325 is T infinity, because this is, right? And then that's like theta naught, and that makes it easier, just more concise to work going forward. So really what we're saying is we have the ln of theta naught is equal to all this gibberish, that stuff, times 0 plus C1. So C1 is ln of theta naught. So I'm going to do all that algebra that I kind of explained before, and you end up with this. Theta over theta naught is equal to minus H A sub S over rho VCT. So we got all that. And then at this point, you solve for T minus HAS ln of theta over theta naught is equal to T. And this is, let me put the minus out in front of this whole thing. Okay, so I'm going to put the minus out in front of the whole thing there. And where was I going with this? So we want to know the time that it takes to cool it to 450 Kelvin. And so at that, at this time, since we know the desired temperature, the theta is going to be 450 minus 325, and theta naught is our 1150 minus 325, and then all this other crap we're given in some way, shape, or form. Remember, like, here's that situation where instead of actually like typing in your calculator the volume and the surface area, you could just kind of go ahead and say that this is going to be LC, which is going to be D over 6 or R over 3, but pretty sure we're given the diameter of the balls, so it's easier, less work if you just do D over 6. Rho, C, H are given. Plug all that in, you get a T, and this should be like 9 minutes. No, what did I? It's like 900 something seconds. I don't know. It's like 9xx seconds. Okay. Like I said, I'm not taking time to punch stuff in the calculator, but you guys can look in the solutions for what the final value is and compare. So that's that one. Okay, so we have what? 3 left. Oh my. Well, I'll make sure to put timestamps in this video so you can skip around and come back to it whenever. All right. So 5.9. Okay, 5.9. We're on to 5.9. So it says the heat transfer coefficient for hydrogen flowing over a sphere is to be determined by observing the temperature time history of a sphere fabricated from pure copper. The sphere, which is 20 millimeters in diameter, is at 75 degrees Celsius before it is inserted into the gas stream, having a temperature of 27 degrees Celsius. A thermocouple on the outer surface of the sphere indicates 55 degrees Celsius 97 seconds after the sphere is inserted into the hydrogen. Assume and then justify that the sphere behaves as a space-wise isothermal object and calculate the heat transfer coefficient. So what that's saying is you're assuming that this Biot number is less than 0.1. That's what space-wise isothermal tells you. How did I know that? Well, that kind of comes back to that discussion that I was having before, where the whole like premise behind these problems is that Biot number being less than 0.1 indicates that you can assume that it's space-wise isothermal, and therefore temperature is only a function of time, which then allows us to actually find some analytic solutions. Space-wise isothermal. So it's a constant temperature with regard to space. The temperature doesn't change as you move throughout space in that solid object. So the temperature at the center is assumed to be equal to the temperature at the surface, and so then we can do everything like we have been doing. And so that's like really the only tricky part in this one. You have to recognize that that's what they're getting at. And if you didn't really, I would advise that you guys, if you're struggling with that concept, I don't really know, maybe reach out to me personally and I'll try to explain it better to you. But I think the combination of the things that I said should make it start to click. But that is something that I advise, do not, like, I think you should, like I said before, you need to really internalize that and understand what that means, so that on the next exam, when these types of problems are mixed in with other types of problems, you can recognize when you're supposed to be doing this method and when you're supposed to be doing whatever else we're going to learn coming up. And so where was I going with that? The cop-out easy approach would be that this is the lumped capacitance section, or this is like the case one, as he calls them, section. And so you just know that that's what we were doing, and so that's how you're going to have to solve it. But I think it's better, well, not I think it's better, it definitely is better to actually understand what's going on, because that's, the heat transfer part is this, really, and then the rest of it is just doing some algebra and solving some doing some basic integrals and math is the rest of it. So let me catch my breath here. With all that being said, we're going to draw a crappy looking circle, even though I have a nicer one over there. Put a control volume around it. Okay, so this is a sphere. Remember, this is a sphere. yes, it tells us it's a sphere in the problem. It's a sphere that has a certain diameter. But I'm drawing a circle because it's easy. Okay, so we got E dot ST. I'm going to go a little bit quicker this time. E dot out by convection. All right, and then remember, if you do the energy balance, I advise that until you get really comfortable with like actually understanding this and not like do not do what I'm doing here with skipping steps if you don't actually understand why you can skip the steps and get down to here. I would advise starting with the whole, you know, do the whole energy balance equation and then cross off the terms that you know aren't there and get to this by actually doing good physics work and understand, or not physics, well, whatever you want to call it. I mean, really, this is all physics, kind of. Doing the good work. This is really embarrassing. I can't think of words. Start here if you don't understand, if it doesn't jump right out to you how I'm jumping right to here. Don't just jump right to here and get into a bad habit of not really understanding things, because then you'll get burned on the next test. Pun intended. Okay, so E dot out convection. All right. This is like pretty much automatic now. The surface area, T minus T infinity. E dot ST is pretty much automatic too. Rho VC dt dt. All right, and so I'm not going to actually solve the ODE this time. So you can, you plug all that in, you do the same type of stuff. And I would advise, I'm only doing it for the sake of brevity and not wasting more of your time. And so you guys can just see like the problem solving parts that are involved in this one. Oh, I forgot to mention. So up here, basically in the problem, and I think I already read this, but I forgot already. We want to find H given these conditions. And so that's why we can't actually calculate the Biot number. And we just have to start by assuming that it's less than 0.1. And then once we calculate the H, then we'll go back at the end and calculate it to make sure that it truly was a good assumption that we made. And so I'm going to skip all the integrals in that business and just know, from before, we have theta over theta naught is equal to minus H AS over rho VCT, right? And our theta naught here is different because our T infinity is different and our T1 that we're given is different. All right, and so, here we're going to do similar to that one we did before. We're going to do some algebra. And we're going to have theta over theta naught is equal to, no, not T. I have T on the other side. What a freaking goofball. This is poor performance on my part. I'm sorry. The T is down here. We want to find H. I know I did that switch quick, but they're on they're both on top on this side, and so we can just, you guys can do algebra. If you can't do algebra at this point, then I'm not the person that's going to be able to help you, because I've tried helping people, tutoring people in algebra before, and I was terrible, and they got really mad at me because I cannot, I guess, I don't know what it is, but I cannot explain it on a level to somebody that struggles with it. So I hope you guys can sift through that part on your own. And I'm sure if you were, you all made it this far, so you can probably do algebra and understand what's going on there if you take your time. Okay, so H is equal to rho VC or minus TAS log. All right, and then at this point, I mean, once again, we know everything that we need to calculate the left side there, and so you just plug the numbers in and you get an H. And then once you have that H, you want to go and calculate your Biot number. All right, and remember, in this case, LC is R over 3 because it's a sphere, or it's D over 6. And so you plug all this stuff in, and you get your Biot number, and it should be less than 0.1. Okay, so now this one's tricky. This one is probably the one that you have to, well, I don't know, the next one's got a little bit of a trick in it too. But this one is where the discussion previously about the whole LC thing, and when you don't actually have enough information to calculate the volume in the surface area, like how, why sometimes you need to understand it more thoroughly. Um, so let me compose myself here before I say something stupid. I've already said enough stupid stuff in this one video. Okay. So we have these cereal flakes, like they're these skinny things, right? And so we have this cereal thing, and a bunch of them are going on this conveyor, and this conveyor goes through an oven. It's got a length L naught that we're given, and we want to find the velocity of the conveyor that's going to allow us to actually cook our and so I should write more of this information. The T infinity is 300 degrees C, and these guys start, or maybe I should say T1, they start at I gotta go look in the book here. They start at 20 degrees Celsius, and we need to get them up to a final temperature of 220 degrees Celsius in order for these cereal flakes to be cooked. By the time they exit this conveyor, this oven portion of the conveyor, they need to have hit 220 degrees Celsius. And we need to calculate based on the temperature of the convection oven there, and basically the convection oven part is taken care of by giving us the T infinity and the H. That's all that you really need to know in that department. We need to figure out the velocity of the conveyor to make this happen. So you come into a problem like this, and it's like, holy crap, like what the frick is this? Like, how the hell am I going to solve this? This is really complicated. I have no clue. This looks like nothing I've ever seen before. But you just got to take a breath and relax. And so if you didn't know that we were in the lumped capacitance section, and you didn't know we were solving problems along the lines of like doing the Biot number, checking if it's less than 0.1 and all that business, if you didn't really know that, and you couldn't just know that that's what we're going to end up having to do, I would start with an energy balance. And so first off, you know that there's E dot out by convection, right? Well, we're just going to call it E dot out. We don't necessarily know if it's in or out, but we're just going to call it out, and the signs will work themselves out. And so now it's a question of what are the other energy terms. And so here, when I get to this point, then I'd say, all right, well, I am curious, especially with how thin these guys are. They're so thin that the temperature change throughout them has to be really small, because there's there's barely any material there to even, for them not to be, right? And so then I'm going to say, all right, well, let me look at the Biot number. Let me calculate a Biot number. HLC over K. And I'm like, all right, okay, I got my H, I got my K. Now what the hell is LC? So you're given 2L equal to 1.2, and that's the thickness of one of these string beans, right? Now they're not string beans, but I was trying to be funny. That was bad. These cereal flakes, right? 2L is the thickness, and it's 1.2 millimeters. All right. And so they're already kind of setting you up to figure out what this is, because it's like, why would they give it to us like 2L? And so you could just, decide like, oh, well, I'm just going to find L, and then that's going to be my LC. The other thing is like I was kind of talking about before, if you think about it, right, we're assuming, like, let's assume that these cereal flakes, like around an axis through the center of them, like if we had like a perfect axis that went through the center of them somehow, that on both sides of that like they're symmetric about that axis, and their heat transfer and all that is symmetric about that axis. And so we really only, like, when we're looking at a dimension that accounts for the spatial variability of the temperature not changing through space, we only care about like half of that, because we know if it's the case in one half, it's going to be the case in the other half, because this is a cereal flake and it's symmetric about its center. And so with that being said, if the thickness is 2L equal to 1.2, then that LC, that half that we care about, is going to be, you divide it by 2, and it's going to be 0.06, which I already have written here. And so you calculate your Biot number, you're going to get something that's really small. It's way less than 0.1. Is you're like, woohoo, I can use my lumped capacitance thing. Okay, so then you come in here and you're like, all right, so now we're going to just think of this as like, we're just going to care about the E.st there. Okay, so this is the same, like literally the same setup as before. And so I'm going to skip all the steps, right? I'm just going to go right to the end that we know that this is going to be the temperature distribution, right? Minus HAS over rho VCT. Okay, so we know our initial temperature, we know the temperature we got to get to, we know everything else, and so we can actually solve for the time now, which is like at the beginning of the problem, it's like, how the hell am I going to figure out the velocity, right? Well, when we get the time, okay, you'll see where I'm going with this. So here, this, I don't know why I wrote that in another color. Theta naught is equal to T. We'll make this red stuff the same color so it's not weird. Okay, so you get the time there, right? And then, you know, I of course already did this, and so I could kind of, you know, I struggled through it a bit, and then I realized what I had to do. You know the distance of that conveyor portion that goes through the oven, and so you can just say, all right, well, I know that velocity is equal to the distance over the time, okay? And so it's L naught, and then you take your time that it needs to cook for, you throw it there, and you're going to get the velocity. And that's that velocity, whatever that works out to be, is that conveyor is going to move at a speed that those cereal flakes are in that oven long enough to experience those energy transfers that we did the balance with to get their temperature up to what they need to be. And then the second part of the problem is that one of your buddies, one of your pals on your engineering team, you get a velocity there in meters per second. You check, you do this and plug the numbers in, and then you check with the solutions to make sure you did it right. Then in like part B, one of your buddies that's an engineer at the cereal company comes in and says, all right, well, let's make the thickness 1.0 millimeters. Because the business people said, we got to be putting out more cereal. You engineers figure out a way that we can produce more cereal. And so your buddy's like, oh, well, if we make it thinner, we can increase the velocity of the conveyor because they'll need less time, because now that they're thinner, the heat is going to, transfer through them quicker, and they're going to increase their temperature quicker because they're smaller. That's all kind of, like you guys probably have an intuitive or like a common sense understanding that that's the case. And if not, the math that we do here can show it, but I'm not going to do that. And so your buddy's like, all right, we can bump up the conveyor velocity if we use thinner ones and still get the same results. And if the conveyor velocity is bumped up, then we're going to be putting out more cereal flakes. So, with all that being said, I'm done blabbing. Basically, you go back and you do the same problem, except now your thickness is 1 millimeter instead of 1.2 millimeters, and you do all the same work that we did above, and then you get a new velocity, and you check, is it greater or not? And I mean, it should be. But before you get into that, you want to be careful that before you go skip this step, you should probably calculate with this new thickness your Biot number. Now, if you're clever, you'll notice that we're decreasing the characteristic length, right? So if this goes, the LC goes down, well, it's on top, right? So this has to go down, and so it's going to be even less than 0.1, and then you're okay. So if you realize that, you don't actually have to recalculate it, but if you need to convince yourself, you can recalculate it and do all the same work, and you get a T, and then you use the T based on the distance, the conveyor, oven size, that the distance that of the conveyor that is covered by the oven, which is 3 meters and is given. You can calculate a velocity. Man, I'm terrible tonight with getting jumbled with my words. All right, so this next one is kind of wacky too. So there's a lot of backstory that might make it confusing and stuff, but really we're just looking at, we have this packed bed of these aluminum, I think they're aluminum, I don't know, whatever. There's these spheres that are all bunched together, but here we're just looking at one of them, right? and there's this hot gas that's flowing over them, and somehow this is a way that they use it to store thermal energy, right? And so I already have the stuff drawn here. I don't know if it says we can zoom it. All right, so once again, the right thing to do would be to calculate your Biot number, HLC over K, and it is less than 0.1. All right, not double, not just, it's less than 0.1. So you guys do that, confirm it. It's a sphere. We're dealing with spheres here, and we're just looking at one of them. So because it says, like, it's asking about one at the edge, and so we can just take one of them and pull it out and look at the one that's at like the very left edge. If you look at the picture in the book, it would be like the very left edge where the gas first hits. So one of these spheres is going to be d over 6, which is r over 3. And now with that, let me gather my thoughts here. Man, I'm tired. I can't think straight. Okay, so you do that and you make sure it's less than 0.1, and we know that this, the way that I'm looking at the energy over here is good. And so, minus E dot out based on that control volume over there is equal to E dot ST. And so we know these already. We did all this stuff before, right? And so once again, I'm going to skip to this step, all right? So we get theta over theta naught. Because I don't have it written here, but you're given the T naught of these guys. What are they? The initial temperature of the spheres is 25 degrees C. And so you can actually, you could use your boundary conditions and plug them in and get that. All right, and this is equal to minus HAS over rho VCT. Okay, so what they ask, though, is how long it takes for the system to accumulate 90% of the maximum possible thermal energy. And then they ask what the temperature is at the center of the sphere, and then they ask if there's any advantage to using copper instead of aluminum. So those last two parts, I didn't realize it when I was gathering my notes and doing these before I got on here and made myself look like a fool. I didn't realize that they were there, and so I didn't do those. So I'm going to be winging those, just doing it live and unrehearsed when we get there. So this whole thing probably sounds like it's not rehearsed, but I did work these out beforehand to make sure I knew what I was doing, and I didn't sound like a jackass when I got on here. So what I'm going to do, and it's going to, I think I should just, I'm just going to start doing it, and then I'll explain why I did it. So I'm going to actually, I want to get theta on its own because, well, I'll start with why. So the total thermal energy that's transferred to this thing, because we just have these two, we just have the E dot out and the E dot ST. So it's actually, it's blatantly obvious that it's E dot in because this gas is hotter than this thing starts at. And so this energy is actually going in. But, like I said before, we can draw it this way, and with the signs and everything, as long as we're consistent and we don't make any mistakes, it works out to be fine. But really, energy's coming in, right? So the total energy that this thing can store is based on what is convected into it. Okay, so we can kind of start there, right? So remember, your convection, Q dot by convection, is HAS times T minus T infinity, right? And this is like your surface temperature. But because of this assumption that we make, the surface temperature is the temperature of the whole thing, yada, yada, yada. And really, another thing is, this is theta, like we saw for above, right? That's theta, okay? So more succinctly, you could write this as HAS theta at any given time, right? So theta here is a function of T in this case, so that's important. And so we take, I want to take this expression and I want to get it as a function of just theta as a function of T. Where right now it's, it's kind of in this wacky form. And so I start by raising both sides, taking, like, doing e to, the exponential, how do I want to, if we, like, a log of x equal to y, the base of this is e, right? So it's really, that's saying like e to the y equals x, right? If you remember that. There's I forget the better way of explaining how the algebra works, but you're going to do that, right? And you're going to get theta over theta naught is equal to, and I'm actually going to write it the old-fashioned way like he does with the exponential thing, because, well, no, we'll do it the hip new way like us kids are used to seeing. HAS over rho VCT. So e to the negative HAS, blah, 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 t. All right, and you subtract the theta naught over. So theta of t is now theta naught e to the minus all this t. So that's theta t. All right, and now, so this q dot up here, remember theta is a function of time here. And so if we want to get the total energy that's convected into this thing over a period of time, we got to use an integral, because an integral is how we add up, like remember an integral is like adding, another way to, and it's a function of t, so it's not constant, so we need to account for that. And so really what we're looking at here is like our total q dot to this thing is going to be the integral of HAS theta of t dt, and we're going to go from 0 to just some time t. Doesn't really matter. And so if you now plug in, right, so we have HAS, and then the theta naught's going to get pulled out. We have 0 to t. This is e to the minus HAS rho VCT dt. Now, the integral of this, you can, technically it's a u, like you would have to do a u substitution. So if you guys need to, scribble that off to the side to make sure you don't screw it up, that's fine. But I'm just going to wing it and do it in my head. And so, like, this, basically this fraction, you're going to have to take it, multiply it out front, and like flip it to account for that. And so this is going to become, and I'm going to keep the I'll save that for the next step. So this is going to be a minus rho VC. The HAS and the HAS on both are going to cancel out. VC. Let me make sure I don't forget anything. Theta naught. And remember I said, like, these guys cancel each other because one's on the top and one's on the bottom. All right, and then that is all times. Now the integral of the exponential is just the exponential t, and this is evaluated from 0 to t. All right, and so you're going to do this and subtract it. I'm going to distribute this negative sign into it too, and so what you end up with is that the q dot is rho VC theta naught times, when you plug this 0 in for t, you're going to get a 1. And it's actually minus 1, but I multiply the negative in, and so this 1 ends up in the front, and then you end up with minus e to the minus HAS over rho VCT, right? Because we just have this, we still just have this t because we're going to any time, okay? And so you have this expression now. And so this is still technically a function of time, okay? But in the problem, they want to know the time that it takes to get to 90% of the maximum. So the maximum is going to be the limit of this as the time goes to infinity. And so what's going to happen there is, as t gets really big here, this negative exponential e to the negative really big power, e to the negative infinity, is going to be 0. And so our q dot max is rho VC theta naught. Okay. I think. Let me just double check that I'm not lying, because this was the one I don't remember if I checked my answers, and this could just ruin my whole video. So hopefully this is right. Oh. Yep, we're good. Okay, we're good. We're good. We're good. Sweet. Okay. So that's the Q max. All right, and then really what we want to know in the problem is when Q is 90% of that. So you need to go back up then, and you're going to say that Q is 0.90 times rho v c theta naught is equal to rho v c theta naught times 1 minus e to the minus hjas rho v c t. Okay, and you're going to solve this nasty, well, so that's going to cancel, okay? And then you're going to solve this whole thing for t. You're going to get t, and it's going to be equal to something, and you guys can check what the number should be in the book, but this is the right math. Or not the book, I should say the solutions. The provided solutions, though, don't solve it the same way. They just use equations that are in the book and like don't explain a lot of steps, and so that's why I thought it would be helpful if I start doing this, because I like work through it, you know, and show you guys, even though I skip a lot of steps, but hopefully this helps. And then at that, you know, at this point now, then they want to know the corresponding temperature at the center of the sphere. And so I think based on the discussion we've had before, it's okay to just say, well, no, it's not. So in the suggested problems, they have some equation that gives you the temperature at the center of the sphere. That's from the book. But I think if we were gonna, no, I'm sorry, I was ill prepared. If you guys want, you can go and look at the solution and see what equation they're referring to there and try to figure it out. But I would think that the right thing to do is once we have this, well, we know the surface temperature because we're like, well, no, we don't. How do I want to say this? We get a T here. You can go back and you can get the surface temperature from our theta thing here. You can get the surface temperature at that time, and then you can use the K, and you could probably get away with like assuming that it's steady state or something like that, and then solve that type of 1D heat convection problem through the that would you'd be like looking at inside the sphere there, and find then the temperature distribution in the sphere if you're like assuming that it's steady state, and get a temperature and compare, and it'll probably be close to what they have there since we're at 90% of the like full value of the heat transfer. So like at that point, assuming steady state is probably going to get you close, but you can see what he does there in the solutions. It's just some equation from the book. And then the copper versus aluminum thing, if you look here at our Q dot T expression, right? So the things that are going to change with copper versus aluminum are your rho and your C, okay? And so copper, the rho C, okay, since this really, this exponent part, since it's a negative here, you don't really have to worry about the rho C term that comes up in there when you're trying to figure out like if it's going to be better or not, because this is going to end up being a small number. And so the thing that really matters is the fact that it's multiplied out front here. And so by looking at it like that, you know that a higher rho times C, is going to give you a higher Q dot T, which, you know, your Q dot max here has that rho C in it too. And so if rho C is greater, basically what I'm trying to say, rho C is greater, then you're going to be able to store more energy. And so you can go and look it up. And if you look at it, the rho C of aluminum is less than the rho C of copper. And remember, rho C is just, you know, density times specific heat, and you can find that in like table A1 or something like that. And so you can compare the values that were given here, because these ones that are given up here are for aluminum. You can compare those that multiplication of that combination to that of copper, and if the copper's higher, then the copper's better. And I would suspect that copper's better because we've talked before. We've mentioned how copper has the highest K of all materials, and so if it's a good conductor, it's going to be able to store that energy the most efficiently because like even though in this case we're not really worrying about the conduction, that still is kind of a way that you can help make it a little bit more intuitive and think about it. But yeah, so that's the last problem. I'm sorry that this took so long, but I wanted to make sure that I was thorough, and I didn't really rehearse this much because I'm already, a couple hours in for getting this whole thing together. So I'm sorry that it's not really polished, and I'm just going to throw the whole video up, put some timestamps on there, and you guys can jump around and process it. And I hope it helps, and I just want to say that any feedback for what you'd like me to do differently, if you want me to keep doing this, all that's going to be appreciated. Don't be afraid to reach out to me personally. And then in the description of the video, I'm going to drop my uh, Bitcoin wallet that I don't have yet, my Bitcoin Cash wallet that I don't have yet, my Ethereum wallets that I don't, all those wallets. So if you guys want to send me cryptos, you can go right ahead as a donation. I'm trying to work on building up my stock of cryptos right now. And so yeah, that's it. So I'll see you guys later. And